pronounce the rest of the name in case I get it wrong. Arrow, and we've got that.
Say that for most of my life I was now I think it's pretty easy to pronounce the very last one. Alright, so I'm going to talk about boundary velocity, boundary vorticity, solutions to the Euler equations. Now, this is work that in better collaboration with an idea by a guy called Philippe Stefani. And the main point of this work actually was to never seen before in PhD, okay? To get a priori estimates. Okay, so this is about how to get existence ranges for generate somehow some sequence of smooth approximations, and then get accurate estimates. And enough accurate estimates to get and the nonlinear for the and so that this will transport the estimates that you have for vorticity, and then through the data upgrade these by 1 incident, better with the velocity. So the velocity gains one derivative on the vorticity through the Biot-Savart law. Okay? So what I'm going to talk about is what happens, how do you get a priori estimates for velocity when you no longer have the Biot-Savart law. Okay? All right. So here are my collaborators, David Ambrose from Drexel University in the United States, Tim Kelleher from the University of California in Riverside, and Milton Lopes Phil, who's sitting here in the audience. Okay? All right, so let me, just for the sake of establishing a study notation, these are the Euler equations for incompressible non-viscous ideal fluid flow in 2D. Of course, the written in velocity formulation, they're no different from the ND version. Okay? Now, here U is supposed to be a vector in 2D, U1, U2, and of course, the nonlinearity is understood as a differential operator U dot grad acting on each component of the velocity. P is a scalar pressure. Okay, so these are the Euler equations. Most of you know them very well. They should be supplemented by initial data, U at time t equals 0, and if there's a boundary by boundary slip conditions, U dot n equals 0, the finite part of the boundary, together with some conditions at infinity. Okay, vorticity for us is the grad perp dotted with U. With grad perp is this differential operator, minus dx2 dx1. And there's only one component of the curl of this velocity vector, 0, 0, omega. So we identify the vorticity with the scalar little omega. Okay, and the vorticity equation in 2D is just a transport equation dt omega plus U dot grad omega equals 0, coupled with the elliptic system, divergence U equals 0, curl U equals omega. Okay, curl U is, of course, stands for the grad perp dot U. So this elliptic system plus some boundary conditions, it's elliptic, and it can in principle be explicitly inverted. Okay, and the inversion is what we call the Biot-Savart law. It's given by a linear operator k acting on omega, which is the grad perp of the Laplacian inverse of this little omega. K is a Biot-Savart kernel, and it depends on the fluid domain. Okay? Of course, it has to depend on the fluid domain because this Laplacian inverse is the Dirichlet Laplacian. Okay? Okay. In all of our 2, the kernel k is given by the perp of z over 2 pi z squared, where z is a vector z1, z2. I'm not sure I wrote that down. No, I didn't. So in particular, it has, at infinity it behaves like 1 over z, and it has a 1 over z singularity, which means that, now this is very important, k is locally LP for small p's, and it's qth power integrable at infinity with q large. Okay? All right. Hence, to calculate the Biot-Savart law applied to some scalar omega, what I need for the integral to converge pointwise, okay, I'd need omega to be an LP prime intersect LQ prime with large p prime and small q prime. For instance, omega is L infinity intersect L1. Okay, and this is known as the Judith space, L infinity intersect L1. Okay? All right, so this is an integrability condition at infinity, which we understand to mean that typically omega has to have some decay at infinity. Okay. So before I go into the main problem, let me tell you a little bit very fast about some well-posedness results. So the fluid domains that we have of interest in this talk are the full plane R2 and exterior domains. Okay. In all of R2, we start very smooth in HS for S larger than 2. Then well-posedness was proved in 1968 by McGrath. In other words, existence, uniqueness, and continuous dependence. Okay, in the Judith space, L infinity intersect L1, existence and uniqueness was proved by Judith in 1963, Might in 1986. In fact, what happened was Judith's proof was in a bounded domain, and Might extended this to all of R2, to infinite domains. And then he had to add an integrability condition at infinity. Okay, this L1, the reason for this L1 is so that the Biot-Savart law makes sense. Okay. Dupern and Maida proved in 1987 existence without uniqueness for initial vorticities, which are LP, compactly supported for p greater than 1. And initial velocities correspond to initial velocities, which are L2 loc. Okay? Again, here you have a condition, a decay condition at infinity. And Becky and Wu proved in 1993 existence. They extended this all the way to L1, compactly supported. And the state of the art is Delors' theorem as far as existence goes from 1991, where the initial vorticity is allowed to be a bounded measure, compactly supported, therefore decaying at infinity, which has a distinguished sign. You can actually add to that any LP function, which is compactly supported, also, irrespective of sign. Intersect h minus 1 so that you rule out Dirac's. This was aimed at the vortex sheet initial data problem. Okay. When vorticity does not have any decay at infinity, in principle, the result that you know is existence and uniqueness for periodic smooth flows. In other words, in the presence of symmetry. Okay? Okay. In an exterior domain, you have the well-posedness for smooth C1 bounded velocities, and with vorticity having some decay. It's got to be L infinity, and it's got to have some moments, which are also integrable. And this, again, is a decay condition at infinity. Okay, some regularity. And then you get well-posedness, and this is a result due to Kikuchi in 1981. Yes?
So uniqueness has not been pushed past the vorticity in the first...
Okay, so this is almost the state of the art as regards uniqueness. Okay, I'm saying almost because this has been extended slightly, but not even all the way to BMO. Okay, it's been extended to these local Judith spaces and to these small BMOs. Okay, that's a result by Vishik. Okay, so in 1995, this brings me to the central topic of this talk. In 1995, Philippe Serfati published an announcement in the Notocras, the compte rendu, in which he stated existence and uniqueness for 2D Euler in all of R2, okay, with an initial velocity which is merely L infinity, and initial vorticity which is also merely L infinity. In other words, no decay at infinity. So this kind of focuses the uniqueness question on the local behavior of the vorticity, which is where I think it should be. Okay. His proof was terse and incomplete, yet brilliant. Okay, and what I want to talk about here is I want to discuss his technique, his method, okay? And so that we can actually publish a paper, we're going to extend this result to exterior domain flows. Okay, okay, so we'll discuss his work. We'll extend to continuous dependence, which is something that he didn't do, on initial data, and to flow domains exterior to a single connected obstacle, an island. Okay, so here's a statement of our problem. Let omega be either all of R2 or the exterior of a smooth bounded connected obstacle. Okay, and I'm going to choose an initial velocity, which is a bounded function on omega, a bounded vector field, sorry, such that you compute its distributional curl, and it's an L infinity function as well. Okay, suppose that this velocity field is incompressible, and if you have a boundary, in the case of a boundary, it satisfies the slip condition on the boundary. Okay. So our problem is existence, uniqueness, and continuous dependence of the solution with this initial velocity. Okay. So there are several questions which come to mind. What do we mean by a solution? Already this is not obvious because, again, many of the definitions of solutions sort of take into account the Biot-Savart law, and I want to stress that in this situation, we cannot write the Biot-Savart law. The integral simply doesn't converge. Okay? What happens to the Biot-Savart law? How do we get uniqueness in this situation? And what kind of perturbations in the initial data are allowed in our continuous dependence result? And what are the norms with respect to which you have continuous dependence? Okay. So let me tell you a little bit about related results. So in 2004, Yasushi Taniyuchi read also Sarfati's proof, and he couldn't understand it, same as we couldn't. Okay, so he provided, he needed the result, existence and uniqueness in all of R2 in this situation, and so he provided a different proof, which is, so the theorem as stated by Sarfati has been completely proved. Okay, however, the proof given by Taniyuchi uses Littlewood-Paley decompositions. Okay, therefore it uses the group structure of R2. Okay, it uses all the symmetry that you have in R2, and therefore it's a highly non-local proof, and therefore it does not generalize to situations in which you have a boundary and there's no symmetry. Okay, in particular, it doesn't generalize to exterior domains. Okay, in 2010, Taniyuchi, together with Toshiro and Yoneda, they were concerned with almost periodic flows in full plane, and they proved existence and uniqueness for a slightly wider class, this thing called the uniformly local Univich space of order theta. Okay, so what this means is the LP norms of the vorticity grow like theta of p, and typically theta of p is log of e plus p, or it's p itself, which would be the case of the Univich space, the standard Univich space. So this space here includes Sarfati initial data. The proof is even more complicated. It relies on, again, Littlewood-Paley theory and on the Boni paradifferential calculus, paraproducts and paradifferential calculus. It's a highly non-local proof, again. Okay, on the other hand, they prove continuous dependence in B0 infinity, meaning that they managed to actually compare the B0 infinity norm at time t of two solutions with the B0 infinity norm at time 0 of the same, of the corresponding initial data. I'm sorry?
So what do you mean by B? What sort of space?
This is the Bezov space.
Bezov space.
Yes, the Bezov space, B0 infinity. Okay, for Navier-Stokes, existence and uniqueness without any kind of decay at infinity has been known since 1999. But in a sense, the problem is easier because with Navier-Stokes, you automatically get, it's easier to get compactness because of the Laplacian. Okay? Okay, in 2009, 2010, Elaine Cozy established the Vanishing viscosity limit of solutions towards the Sarfati solutions in the full plane. There were some conditions for sufficiently short time, etc. And actually, she's got a new preprint out this year in which she improves this result. Okay, but again, this was done sort of without looking at the Sarfati technique. Okay, so why do we care about vorticity without any decay? So the first reason is that the main uniqueness result that we know of, which is the Univich result, okay, all the others are sort of minor improvements on the Univich result, is uniqueness for L infinity intersect L1, and as I've stressed already, the only reason for the L1 hypothesis is to have an integrability condition at infinity. And the point is that I believe uniqueness should be strictly a local issue. You shouldn't care what what's happening at infinity, okay? What the vorticity is doing far away. Okay. Furthermore, the assumption of decay of initial vorticity at infinity is not physically natural, okay? Because again, our flows really, I mean, infinity is just an artifice, of a technical artifice, so that we can deal with things. But really, the flows that we care about are local flows. Okay. Okay. So, in light of the Taniguchi, Tashiro, and Yoneda's work, why should we revisit Serfati's proof, given that now we do have proof in all of our two? And the reason is, first of all, Serfati's proof is a local proof. It's a simple idea. Okay. It's local. And therefore, it has broader potential application, okay, including extending it to the situation where you have boundaries. And furthermore, it's interesting to understand this idea of substituting the Biot-Savart law to gain compactness. This may have applications in other PD. Okay, so the key idea is what we refer to in our work as Serfati's representation formula, although he didn't write it as such, okay? And let me explain to you how it goes. So you consider a smooth cutoff function, A epsilon of the origin, and this is going to be a cutoff. The role of this is a cutoff for the singularity, okay, of the Biot-Savart kernel, okay? In other words, A epsilon is 1 for small z's near the origin, and it vanishes for large z's, okay? And we establish a formula, or Serfati actually, establishes a formula like this. So u at time t at a point x is u naught at x, plus this is an integral in space, and R2, a epsilon times k at x minus y, times omega t at time t point y minus omega naught at point y, dy, minus the integral from 0 to t of the integral over all of R2 of u of sy, a second derivative of the term 1 minus a epsilon of x minus y, k of x minus y perpendicular dot u of sy dy ds. Why? The main point is that all of the terms in this formula converge. Okay? So indeed, in this first integral, if you assume that omega is merely bounded, what you've done with this is to localize things near the singularity of the kernel k. Kernel k has a singularity which is like 1 over z. Okay? So 1 over z is integrable for small p's locally, and what you've done is, by multiplying by epsilon, you've just localized where it is integrable. Okay? So a epsilon times k is L1. Omega is L infinity. Therefore, this integral pointwise converges. Okay? In the second term, you have u here, u there. Suppose that you know that u is L infinity. Then you can bound this in L infinity, this in L infinity, and the main thing is that when you take two derivatives off of something that decays like 1 over z, you get something that goes like 1 over z to the cube. And 1 over z to the cube is integrable. It's L1 in R2, near infinity. Okay? So in 2 dimensions, the stuff in here is also integrable. Okay? Okay. So now let me tell you where this formula comes from. How do you obtain this formula? So you suppose first that you could write the Biot-Savart law. Okay? Of course you can't. We know that you can't in the situation of interest, but we'll be able to approximate the situation of interest by objects for which you can write the Biot-Savart law. Okay, so suppose u is smooth bounded, a classical solution, and omega naught is compactly supported. Of course, omega times t will also be compactly supported. Therefore, u is just a Biot-Savart law applied to omega at time t. So if I take a derivative of this with respect to time, I can put this derivative on the integral, and then I will put it alternately. I will separate my kernel k into a epsilon times k plus 1 minus a epsilon times k. Okay, and at one point I put the time derivative outside of the integral, Then I take the time derivative and slap it onto omega. So if we integrate in time this expression, we get the integral of dtu is u at time t minus u naught. The integral of this first term here is just this integral evaluated at time t minus whatever it is at time 0. So I get this term, and plus I get the integral of time of this second integral here. Okay, here we go. So let's look at this last term. Okay? Now, before I integrate in time, I can substitute dt omega. This is an exact smooth solution of the Euler equations. So I just substitute dt omega by minus u dot grad omega. And I remember that u dot grad omega comes from taking the curl of the nonlinear term in the velocity formulation of the Euler equation. So this is minus my 1 minus a epsilon k times the curl with respect to y of u dot grad with respect to y of u. So I integrate by parts. I first take the curl and I slap it onto 1 minus a epsilon times k. So I'm going to get the first term here graded of this guy perp. And then I take my u dot grad and I put it onto the rest. So I've got u dot grad of the gradient of this vector field perp dotted with u. Okay? And then I substitute this, integrate this in time to get the Sarfati identity. Here it is. Okay. Now, why is this useful? Okay. This is the identity which substitutes for the Biot-Savart law. Okay? And it's useful because from it we can derive a priori estimates in L infinity. So in order to explain this, let me start explaining a little bit the strategy to get existence. Okay? So you start with an initial data which is L infinity, whose initial vorticity is L infinity. Then you construct a sequence of approximations, and that in itself is not trivial, because you have to construct a sequence of approximations which are reasonably smooth, such that the corresponding vorticities are smooth, and these guys are compactly supported. The omega naught n's are compactly supported. You want this to converge uniformly to the initial velocities to converge uniformly, and of course, since this is compactly supported and the corresponding vorticity isn't, you don't get uniform convergence for the vorticities, but you get convergence in LP for any p on compact sets of R2. Okay, so we get a sequence of approximations satisfying this estimate. Solve 2D Euler with the initial velocity u naught n, denote the solution by un, and then use the Sarfati identity to get L infinity estimates for omega n, for the vorticities, and for the velocities. And that's where the Sarfati identity or Sarfati representation formula comes in handy. Okay. After this, you use the L infinity estimate for un and for omega n to prove, at this point it's really a standard argument. You use this to get the log Lipschitz continuity of the velocities. Okay, from the log Lipschitz continuity of the velocities, you get convergence for the flow maps, the particle trajectories xn, and then to some limit flow x. You show x is measure preserving. You define the limit vorticity to be the transport along these flow maps, and then you have to show that your sequence of vorticities converges to this limit vorticity, and L infinity locally in time, LP locally in space, for any p less than infinity. And then finally you show un converges uniformly on compact sets of space-time. Afterwards, you still need to go back and show that u and omega satisfy the incompressible Euler equations in the sense of distributions. The vorticity is transported along these particle paths, and most importantly, your solution will satisfy the Sarfati identity. Okay? The limit is log Lipschitz. Okay, so the main non-standard point here is exactly the compactness is how you get the a priori estimate in L infinity for the velocity in this existence proof. And I want to illustrate this. This is the main use that we make in Sarfati identity. Okay? So I'll work on the full plane, and I start with the Sarfati identity and simply throw absolute values everywhere. Okay, so I get the L infinity norm of u at time t will be bounded by the L infinity norm of u at time 0 plus the supremum for all x's. So here we have, I simply put an absolute value in all the terms in my Sarfati representation formula. So it's the sup of the integral of a epsilon times k times omega t minus omega naught plus the integral in time of the supremum in x of the integral with the second derivatives onto the Biot Savart kernel. Okay. So this term is L infinity norm of velocity. I can pull out twice the L infinity norm of the vorticity because, again, that's being transported by the flow, okay, times the L1 estimate of L1 norm of A epsilon times K. I didn't tell you who A epsilon was. A epsilon is just a rescaling of A. So you take A of x over epsilon, okay? So the support of A epsilon is going to be in epsilon neighborhood of the origin. Okay, and then here I'm going to get the L1 norm of the second derivative of 1 minus A epsilon K times the integral of the L infinity norm of U squared. Okay. In the full plane, it is very easy to check that the L1 norm of A epsilon times K behaves like constant times epsilon, and the L1 norm of the second derivative of 1 minus A epsilon times K behaves like constant over epsilon. Hence, the a priori estimate that you get from doing this, play is this. It's L infinity norm at time t bounded by L infinity at time 0 plus a constant times epsilon plus constant over epsilon times the integral from 0 to t of the L infinity norm of U squared. Okay. You choose a convenient epsilon, which is 1/2, which is the square root of this quantity, and you get, and then you square everything and you get this inequality here, which is very good because now we can use Grunwald inequality and get the desired L infinity norm, L infinity estimate for velocity. So that's how you use the Serfati identity. Yes?
So it looks like what you did might be robust with...
I'm sorry, I couldn't hear.
It looks like what you guys are doing here might be robust with Navier-Stokes.
We are checking into that, actually.
Because it looks like you're just...
For Navier-Stokes, the whole problem is what do you do with the particle trajectories?
Right. So you have to use a completely different compactness approach.
Okay, so let's see. For Navier-Stokes, I think the L infinity norm is not an issue. It's not going to be a problem, okay? But the whole point is that, so let's see. Let's go for Navier-Stokes.
I think I noticed that you had just used only the structure that you had taken second derivatives of that second kernel term, which looked like then you were fine with.
What I need to do is, you're right, yes. Okay, the main issue for Navier-Stokes is the uniqueness, is how the uniqueness proof goes. Okay, so I will show you that. You're right, sorry. Okay, yes, okay. Okay, so how do you extend this to an exterior domain? Okay, but I mean, existence for Navier-Stokes is the whole thing is much easier because you have the Laplacian term to play with, so you don't need the Biot Savart law for Navier-Stokes. Okay. First of all, we assume the domain is exterior to the unit disk. Okay, and so we no longer have a convolution in the Biot Savart law because there you can explicitly compute the Biot Savart kernel, and it's given by the Biot Savart kernel for all of our 2 minus through the Biot Savart kernel with respect to the image point y star. So this is the unit disk, and y star is y over y squared. It's the inverse with respect to the unit circle. Okay, so from previous work, we know that actually this guy doesn't behave like the, in terms of estimates and decay, like the Biot Savart law. The thing that does behave like the Biot Savart law in all of our 2 is when you add a point vortex at the origin, which is not there in my exterior domain. Okay, so I'm adding k of x, which is x perp over 2 pi x squared. Now this guy here behaves like k of x minus y in terms of estimates. Okay, so I'm going to add this point vortex and denote this by j. This is also known as the hydrodynamic Biot Savart kernel in some circles. And there's a downside, which is that k actually vanishes on the boundary. Okay, so for y is on the boundary. But j does not vanish on the boundary because you've added this extra term, k of x, which is independent of y. But you still play the same game, and you arrive at a new Serfati type identity, okay, which is given here. And now there's a boundary term, which is k of x over 2 times u squared gradient of a epsilon d sigma. And it turns out that this is just as useful as far as getting the upper estimate in L infinity as the original one was, okay, in all of R2, because this J will observe the same kind of estimates as we had for K. In other words, when you localize, you get something localized with and scale with respect to epsilon. You get an L1 norm, which goes like epsilon, and then near infinity, the second derivative will behave like constant over epsilon in L1 also. Okay? And then this extra term that you get from the boundary, this K here is just going to be bounded. Okay, it's like 1 over x is larger than 1, so this guy is bounded. And here you're going to get an integral in time of the L infinity norm of u squared times something which is like 1 over epsilon, because it's the gradient of the rescaling. Okay? So you again get c over epsilon times integral in time of the L infinity norm squared, and you're back to where you were before. Okay. Now let's talk about uniqueness. So suppose you have two solutions, U1 and U2. Okay? You again use the Serfati identity, but here there's a problem in doing this for Navier-Stokes. Okay? So suppose you have, so the idea is look at the two different particle trajectories, x1 and x2, each one associated to the different solution. Suppose they start off at with the same initial data and at the same point. Okay? The strategy is to show that the particle trajectories coincide, therefore the vorticities coincide because the vorticities are simply transported along particle paths, and therefore the velocities coincide. Okay, so you use the Serfati identity to estimate the derivative in time of x1 minus the derivative in time of x2, which is u1 at x1 minus u2 at x2. And I think I'm going to skip this because I'm actually doing this in a lot more detail in the next transparencies, the next slides. I do want to point out that I will need the modulus of continuity of u, which is log Lipschitz. So velocity is a log Lipschitz function, okay, meaning that u of x minus u of y is like the log of x minus y times x minus y plus 1. Okay? And so I'm going to choose a modulus of continuity, which is an increasing function, and which goes like h log h. And h is going to be the difference, the L infinity norm of the difference at time t of along each particle trajectory, which I want to show is 0. Okay? Okay, I think I introduced these later. So let me go through the steps in the proof of uniqueness. So we start by defining h, which is the supremum of the distance between the two particle trajectories, and I want to show that that's 0 for every time. I'm going to bound u1 at x1 minus u2 at x2, and then h actually is going to be bounded by the integral in time of this of h of s. Okay? Sorry, the integral in time of this object here. So by the triangle inequality, I can split this into two pieces. I'll insert a u2 at x1 here, and so that I can bound this term here by the log Lipschitz modulus of continuity of u2, and then I have u1 minus u2 at the same point, x1. Okay, so there it is. So this is bounded by mu of h, and this is u1 at x1 minus u2 at x1. Okay, and then I will look at this term in blue. For this, I go back and use the Serfati identity again. Okay, and I get that this is bounded by the following two objects. So first of all, the initial data goes away because it's the same. Okay, and I1 is the integral corresponding to the localized Bezoar kernel, and I2 is the integral corresponding to the stuff near infinity. Okay, times, and then I'm going to get u1 tensor u1 minus u2 tensor u2. This is at x1 of sx. This is at x1 of tx. Okay. Okay. So then I have to change variables Lagrangianly, and that's where we run into trouble for Navier-Stokes, because you don't have vorticity transported any longer along particle trajectories, and we can show that this term I1 is bounded by a constant times h log h times L infinity norm of the initial vorticity. And this term, this is the most difficult step, in particular in an exterior domain. Okay, this is where you really have to get down to the nitty-gritty of the kernel K in an exterior domain. Okay? So I1 is bounded by mu of h. Okay, as for I2 is the integral involving the second derivatives of k and minus times u1 minus u2. And here it is. It's a whole bunch of yucky stuff, but it's pretty natural because I'm going to put this guy in L1. Notice I don't need any rescaling of a's anymore here. Okay, and then I have times the L infinity norm of this difference here. And this difference here, you can actually factor out a u1 minus u2 and use the hindsight that you already know you have an L infinity solution. So u is bounded in L infinity, so you get something involving simply the difference in L infinity of u2 minus u1 at the same points, x1 of s. Okay? All right. You again play the triangle inequality business, and you get the integral in time of mu of h plus what you started off with. Okay? So we put everything together, and there's an h here that shouldn't be here. Let's see. So in the end, what you get is this. You get the L infinity norm that you wanted to work with, which is the bound that the integral of p is what bounds h. Okay? So p is bounded by constant integral of mu of h plus a constant times mu of h plus a constant times the integral in time of p. And let's see. You end up with this ground wall type estimate. M prime is bounded by this chunk, which I will call nu of m here, okay? And nu is Osgood continuous, meaning it's non-integrable near 0. 1 over n is non-integrable near 0, the same as h log h. It's the same kind of behavior as h log h. And therefore, by Osgood's lemma, okay, this means that m has to be 0 because m is initially 0. Okay? Therefore, p has to be 0 because m is an integral of a non-negative quantity. And therefore, h has to be 0 because h is bounded by the integral in time of p. The end. Okay. So we need to summarize everything and introduce a proper notion of weak solution in this case. And I'll start with what we're calling the Sarfati space, which is simply L infinity of u plus L infinity of the vorticity. And I'm going to say that this, if you live in this space uniformly in time, then you're a weak solution if you satisfy the incompressible Euler equations in the distribution sense. Okay. You have to have the Sarfati identity holding for all cutoff functions A. And the reason I need that is because in the existence argument, there's a point where I have to rescale A. So I need to have this for every single A. Okay? And the vorticity is transported by the flow. Okay? And just a note here, just to stress that such a velocity has a log Lipschitz modulus of continuity. It's a consequence of this definition. Okay? All right, so with the setup, the main result that we have is if you have a smooth domain exterior to a connected bounded set, or if also the Sarfati case where you're in all of R2, then there is just one and at most one weak solution of the Euler equations in this precise set. Okay, with initial velocity u0. Okay, yes?
The boundary condition is taken care of by that last term in
the boundary condition is taken care of by k. Once you write down, so the Biot of our kernel adapted to a domain, okay, automatically gives you that it's tangent to the boundary. So of course, we don't get that, okay, we don't have the Biot of our law valid, but in the derivation of Sarfati identity, it's there.
But it's it showed up as that last term.
Sorry?
It showed up as that last term as an integral on the boundary?
No, it shows up when you write k, it's implicit there. Okay? And the truth is, so for the approximations, it's going to be true. And since the approximations converge uniformly, it's true for the limit. Okay? Okay. So what about continuous dependence on initial data? So we have the following horrible-looking theorem, which the upshot is, if you take two solutions corresponding to two initial datas who are small in the Sarfati space, and this p here refers to any p between 2 and infinity, in particular s infinity, which is the case that we want. okay? Omega in L infinity and U in L infinity, divergence U is 0, U dot n is 0. So if they're small in the Serfati space, then at time t, they will be uniformly close together. The velocities will be uniformly close together. So what the statement that we really wanted was the L infinity norm of U1 at time t minus U2 at time t is little o of 1 as s goes to 0. Okay? Converges to 0. Okay, what's uncomfortable about this statement is that you're measuring the initial data in the Serfati space, but you can only measure the distance between two corresponding velocities at time t in the uniform space L infinity. Okay, so you cannot do this in Serfati space. You cannot put two Serfati norms, okay, on each side.
For finite time, right? I mean,
I'm sorry?
The CT, I don't get it. I mean, it's L goes to 0. As long as L is positive, you have, S0 is positive, you have S0 e to the CT.
Yes.
So it looks like it's blowing up to me.
It blows up, but we're talking about something that's up to some time t.
Up
T
to
is
some time
fixed.
T, yeah. That's
Yes.
Right.
Okay. T is fixed. Okay. So, I'm going to add a few concluding remarks here. First of all, what I showed you, I announced this as exterior domains, exterior to any smooth bounded obstacle. Okay, and then what I actually showed you was how the calculation goes in R2 and the exterior of the unit disk. Okay, so how do you work it out for a general island? You need to bring in the conformal maps. Okay, so you need to bring in knowledge of the conformal maps, the fact that these conformal maps you'll map the exterior of the island to the exterior of the unit disk, and then all of the derivatives are bounded, these conformal maps. Okay? But it works very nicely. Okay, we should try to improve continuous dependence to be able to compare apples and apples instead of apples and oranges, which is what we're doing at this point. Okay? We know that it's basically impossible to compare things in the Serfati space on both sides. Okay? But we would like to get something, a local result, where you would compare the same norms, something intermediate between L infinity and Serfati. Okay, and we're assuming that the vorticity is also L infinity. So that's what happened with the B0 infinity space. It sort of sits between L infinity and Serfati. Okay, but then even to define these Bezoff spaces, actually you need to have this R2 structure, this Euclidean structure. So we only know how to do this in the full plane by Littlewood-Paley. Okay? So there's one very natural question for somebody who does fluid dynamics, which is, what about the vortex dynamics point of view? So we really don't care what the velocity is. We want to be working with the vorticity. So the basic question is, what kinds of vorticity will give rise to Serfati velocities? Okay? So instead of starting out with a flow U0, let me start off with a vorticity U0 and ask, which kinds of vorticity will give rise to bounded flows? Okay? So clearly, if you take, for instance, the most obvious example, which is constant equal to 1, then the velocity is not bounded. Okay, the velocity associated to curl to curl 1 grows linearly at infinity. Okay, so it's not Serfati. So here are some examples of Serfati flows, all smooth doubly periodic flows, okay, which are U0 doubly periodic as well. So for this I need in particular integral 0 for the vorticity. And if I add a compactly supported function to that, that will not change. Okay? So in other words, I can take any compactly supported perturbation of a periodic flow and I can get existence and uniqueness for that. Okay? And I know that it'll stay close at L infinity to the periodic flow. Okay, look at x perp over norm x. The vorticity corresponding to this is 1 over x, and 1 over x is not L1 in the full plane, and therefore, in the exterior of a circle, and therefore the Bezoff-R law cannot be written. Yet, at the exterior of the unit disk, this is bounded, and therefore this is a Serfati flow. Okay? So this is another situation in which you can use the Serfati existence and uniqueness result in the exterior of a unit disk. Okay. This is not that much fun because you still have some decay at infinity. Okay, there's some integrability for the vorticity, and now let's look at an example for which you really have, honest to goodness, no decay, and it's not doubly periodic, and it's not a perturbation of anything which is doubly periodic. Look at the vorticity being the characteristic function of a strip that lies, say, outside or above maybe your obstacle, okay, in the plane. The velocity will interpolate linearly between 0 below the strip to constant, parallel, and above the strip. Okay? For instance, take the strip x2 between 2 and 3, then the corresponding velocity will be 1, 0 for x2 greater than 3, 0, 0 if x2 is less than 3, and x2 minus 2 for x2's between 2 and 3. So clearly that's bounded. Okay? Okay, the end. Thank you.
Questions?
Yes.
I actually looked at your paper a bit this summer for the following reason. Have you guys thought about statistically stationary solutions? Because I think in turbulence sometimes you want to assume spatial homogeneity, and if you do things in the whole space, you know,
we have not thought about that. That's a very nice idea. What we've been working on is trying to adapt this to Navier-Stokes, but it's not easy.
I think that from the point of view of turbulence, it might be an interesting thing to see if.
Thank you.
Just out of curiosity, in which way was the original Sarfati proof incomplete?
The uniqueness proof was really botched. Really botched. I mean, there was a whole bunch of calculations that there was no way of making them rigorous. There was a seed of an idea there, but that was about it. Yes?
It is the almost periodic data.
Almost
periodic. Almost
Almost
periodic
periodic.
data that you mentioned in earlier slide,
Yeah.
right? What's the relation of that kind of data with the data you talked about?
I couldn't hear what.
Okay.
So the question is almost periodic flow, the Tanucci and company work.
Yes. Yeah.
Okay, so Tanucci and al's almost periodic flow is not just a compactly supported perturbation of something which is periodic. It's something which is really quasi-periodic. So in almost every cell, it's like you have a small perturbation.
Can your technique apply to that data? Can your techniques apply to almost periodic data?
Certainly. Yeah. Certainly. But in a sense, we go beyond that because we can do it. I mean, you can have something which is periodic, okay, and then you can perturb just one cell, and the result is that the perturbation, the new solution, will remain close at least in L infinity to the periodic flow.
Yeah.
I was going to ask one other thing. You mentioned other PDEs. Have you tried this with something like SQG or?
No, but we're hoping to. This is still pretty new for us.
Thank you very much indeed.